now we're going to look at connecting together capacitors with different values. So the example I have shown here are a 1 farad, 2 farad, and 3 farad capacitor connected in what is called parallel. Now, the definition of parallel is that whether it's capacitors or light bulbs or resistors or any electronics component is said to be in parallel when the voltage across the devices is the same, and the voltage across the device will always be the same if it is only wires and metal touching metal that connects them. So here, as you can see, I'm starting at the positive terminal of our 10-volt battery as our example, and we have a wire. Now, my right hand turn here is nothing more than just bending the wire. So it's still metal on metal, and I have another wire I solder in here, connected to the top plate. I keep going, wire, solder a wire, connect it to the top plate. So all the same metal touching metal, same color, same voltage. All of these are at 10 volts, 10 volts, 10 volts. And then the bottom plate, which is connected to ground, is at 0 volts. And it's all just metal touching metal. So I find it enormously helpful for you at this point to either use dark lines and light lines if you're only using your pencil, but if you have colored pens to use, enormously helpful because same color, same voltage, and they are in parallel when the same voltage is across. So now we know for each of the individual capacitors, as it shows down here, Q1 equals C1. Technically it would be times V1, but I dropped the subscript because they're all the same voltage. So Q1 equals C1 times V, Q2 equals C2 times V, Q3 equals C3 times V. So the total charge we have then is just summing up the three charges, Q1 plus Q2 plus Q3. The voltages are the same. So the voltage I can factor out, right? So the voltages are all the same. So the total charge is C1 plus C2 plus C3 times V. So that if we had 10 volts, we could do our calculation. This would be a total of 60 coulombs of charge. Now, what we call the equivalent capacitance is the capacitance that would be equivalent to using one capacitor in place of all three. So instead of using all three capacitors, what would be the capacitance of one capacitor, so that if the battery could talk, right, the battery would tell you the same thing is going on. So whether I have the three connected in parallel or you put just this one capacitor in here, I'm seeing the same thing. Well, if you look at what we have, the equivalent capacitance then would be Q total divided by the voltage. And my Q total we just saw was C1, C2, C3 added together times the voltage. The V's will cancel out, right? So my equivalent capacitance is going to just be, as it shows down here, highlighted, right? C1 plus C2 plus C3. Capacitors in parallel add. And that, I think, is very intuitive based on how we've talked about the capacitance for the parallel plate capacitor, right? So let's just look at that real quick. So the capacitor for the parallel plate capacitor is kappa epsilon naught A divided by D. And here what we're doing is really making a really big top plate because these are all connected electrically. So I'm taking all these top plate areas and making just a bigger area. So it should make sense that when they're in parallel, we really physically make a bigger capacitor, C1 plus C2 plus C3. So please pause the video here, get this down, and we'll talk about another type of connection, the series connection.